Okay, hello everyone. I'm Jack Salgado. I'm a student at Open High School, and I'm here with Secure Futures to do a presentation on uh, physics of solar panels. So this presentation is on indirect versus direct band gaps and how a indirect band gap is less efficient than a direct band gap. Okay, so to begin, we're going to start with what a band gap is. A band gap, or the term band gap, refers to the difference in energy between the valence band, which is the outermost shell of electrons, and the conduction band, which is kind of a free flow of electrons between atoms. We are specifically talking about the highest amount of energy an electron can have in the valence band and the lowest amount of energy an electron can have in the conduction band. And when you subtract those two numbers, you get the band gap. And on the image on the top right, on the left, sorry if that's a little confusing, but on the edge on the left, when there's a large band gap between the valence and conduction band, you have insulator, where electrons generally stay in the valence band because they don't have enough energy to jump between the band gap, which isn't useful for creating electricity. And on the right, when a band gap is very small to the point where it's zero or less than zero, you have a metal where electrons can move freely in the conduction band, but it's also not useful for generating electricity. So when there's a small enough band gap between the valence and conduction band, you have a semiconductor where electrons can jump between the valence and conduction band with the help of outside energy, such as a light photon. And we're going to specifically be focusing on semiconductors due to the fact that they play a major role in generating electricity. So certain semiconductors, when exposed to light, its electrons absorb the extra energy, allowing the electrons to jump from the valence band to the conduction band, which generates an electric current. And band gaps are relevant in this due to the fact that light is a spectrum and not all light has the same amount of energy. So typically you want a smaller band gap so a photon with less energy can help an electron jump between the valence and conduction band, meaning that the smaller the band gap, the larger the spectrum of light you can use to generate electricity, which increases the efficiency of a solar cell. And that is the basics of how band gaps work. So on this slide, we have two graphs, which is a visual representation of direct on the left and indirect band gaps on the right. And what makes the difference between these types of band gaps is the momentum of electrons, represented by K on the x-axis, and you can see energy the electrons have on the y-axis. And as you can see with direct band gaps on the left, it isn't necessary to change momentum for an electron to jump from the valence band to the conduction band, meaning it only needs a photon or light energy to jump between the two bands. But with an indirect band gap on the right, the maximum amount of energy of the valence band doesn't occur at the same momentum as the minimum amount of energy on the conduction band, meaning an electron has to gain both enough energy and momentum to make a jump. And an electron can do this or gain the momentum with the addition of a phonon, which is a vibrational energy that is typically found in crystals. So this overall means that direct band gap semiconductors use less energy to generate electricity because they only require a photon to make a jump, while a indirect band gap semiconductor uses more energy due to the fact that they require a photon and a phonon. So overall, a direct band gap semiconductor will be more efficient. So here we have a list of different materials and their band gaps. This is a table from the University of Cambridge, and it lists different types of materials, what type of band gap they have, and the band gap energy in electron volts. And as you can see, some of the lowest band gaps on this chart are from direct band gap materials, which is the goal for achieving higher energy efficiencies. A notable example of the difference between these types of band gaps are the materials silicon and indium antimonide. Silicon has a indirect band gap that takes 1.12 electron volts to make a jump, while indium antimonide has a direct band gap that takes 0.17 electron volts to make a jump. So the big question is, why aren't these direct band gap materials used more frequently? At the moment, 95% of solar panels use silicon to generate electricity. This is due to the fact that silicon is just extremely abundant. It is the second most abundant material in Earth's crust, right behind oxygen. And in addition to that, solar cells have a high enough efficiency paired with a long lifespan and low cost. Silicon solar cells are simply cheap and effective, although they aren't the most efficient, they still dominate the market. And if direct band gap materials ever want to compete with silicon solar cells in commercial power generation, they need to be cheaper and easier to manufacture. Currently, direct band gap materials are mostly, almost exclusively being used for space travel and for certain military drones. And this is because these solar panels are higher cost. And in these types of technology, they just need an insanely high power generation efficiency, and they don't care about the high cost. And they do this by using junction solar cells, which basically uses different materials, various band gaps to use the widest spectrum of light they can to generate electricity, which is an incredible method, but it simply isn't cost effective. And if we want to power our homes and businesses, then with these types of materials, then engineers and scientists will have to push the technology further. And that's basically it for this presentation. All I have to say is I'd love to help push these technologies further. This summer, I'm continuing with Security and as a technical research assistant, so I can learn more about this field and gain experience. And after this summer, I'm hoping to go to a college with a good engineering program, so I could become a mechanical engineer and continue to work with renewable energy. And that's all I have today. Thank you so much for listening. This was a great presentation for me to learn. And yes, thank you so much.